Very good morning to all of you. Thanks for being here and listening to my defense. Special thanks to Roy for all his guidance and hard work and patience, etc., etc. And Leo, who was the one who initially introduced this topic. So today I'm going to speak about my work, which is about two-dimension spreading for doubly dispersive channels. The motivation for this work has been the need for transmitting high rate data over wireless, and that is what we are going to talk about initially. Then we shall talk about a specific system which was introduced by NTT-DoCoMo called VSF-OFCDM, in which they introduced this notion of two-dimension spreading, which we will talk about. Next, we will focus upon an analytical model to really understand and analyze the advantages of two-dimension spreading. And then we will talk about optimal resource allocation, like rate and power, under different scenarios, like what's the optimal resource allocation if the transmitter is aware of the channel conditions, possibly due to some receiver feedback. Then we'll consider the case when such accurate feedback case is not possible, and what's the best that the transmitter can do. And then we'll give some points of perspective here. As we see that broadband mobile services are becoming increasingly popular. Unlike the previous generations where applications were mostly voice driven, the future applications is going to be data driven, which requires the need for high rate, reliable communications. I mean, I just have some typical figures over here. Like in 3G, there's a need for 2 megabits per second peak throughput, and this is expected to increase to as much as 100 megabits per second peak throughput. And remember, this is all over wireless. So what's the problem? The problem is the channel. As we all know, the channel dispersion increases with data rates. And just to give you some idea, like these are some known parameters. If Tm is the RMS data spread of the channel, and if Bd is the Doppler bandwidth, this factor Tm times Bd is the indication of the channel spread. That is how much the channel is frequency selective and how much it is time varying. And we know that for such high data rates, this product is much greater than 1, which means it's called doubly dispersive. So the dispersion is quite great. And this is just a typical figure. You see, in this figure we send an OFDM signal, and this figure plots the received SNR distribution. And as you can see, the channel gains depend on the tone, the OFDM tone, and also the exact time instant. So this is what I was trying to say, like a channel is dispersive, that it depends on the exact frequency content and also the time instant. So a possible solution, as we all know, is to transmit over parallel subcarriers. Take a high rate data and transmit them over parallel subcarriers with low rate, like OFDM does. But there are several important things which an OFDM kind of signaling precludes. Like OFDM signaling puts different data in different subcarriers, and this precludes the possibility of putting the same information over several subcarriers and thus gaining some frequency diversity benefit, which might be very important for some applications. Especially if the channel is bad, I would like to get such an advantage.
Excuse me?
Yeah.
Why can't you put the same data on two OFDM carriers by using, say, repetition code? Just put 2 bits.
Yeah, I can, but in typical OFDM applications, I mean, that's more towards moving what VSF-OFCDM does. I mean, in principle I can, but in commercial deployments. And also, multiplexing is difficult in a subcarrier. Suppose I want to put the information of 2 different people over the same subcarrier, it's difficult. And such a situation may arise if we consider 2 users who are in 2 adjacent cells sharing the same OFDM tones. So
it sounds like a general answer to Leo's question. Could you ask the question again and you answer it again? Your question was, what can you do?
Well, my question was to his remark that in OFDM you cannot put the same bits on 2 carriers. So I will ask why.
Yeah, and your answer was?
Well, we can, but I mean, in most OFDM applications, it's taking one serial data stream and putting different symbols in different subcarriers and doing the ISFT. And whereas I was trying to say in the new scheme which I proposed, that kind of that kind of putting different data in different streams is inherently a part of the scheme. Yeah, in principle we can do the same way. But
That must be
that's
really
not,
important to call.
that's not what is normally done.
Okay, it's not what's normally done, but
In principle it can be done.
Right, and that's
But
really
in principle, that's what you're doing, right?
In my view.
No, what you're proposing
Yeah,
to do
exactly.
is what he.
right.
If I understand correctly, the biggest advantage of this OFCDMA is actually in case of for the multi-users. So that's a very natural way of separating multiple users. In single carrier case, in single user case, there is almost no advantage. In multi-user case, it just becomes CDMA in frequency. So
Yeah, the more important thing is the second
Provides
point.
you-
Like if I have two users sharing the same clones in adjacent cells, using OFDM transmission, there's a lot of
average is interference.
Yeah.
OFDM provides spiky and interference.
So now I would like to talk about this scheme which was proposed by NTT-DoCoMo for the next generation wireless systems. It's a big acronym. VSF-OFCDM, which stands for Variable Spread Factor, Orthogonal Frequency, Code Division Multiplexing. And this was introduced for the next generation cellular systems and also serves as a MAC for multiple users. So what is it? We shall see that in the next slide. So here I have a very conceptual diagram. So the way we have,
What is the closest sort of model to this one in the past theory?
in the past theory,
Yeah, like do you remember CDMA, and then
I won't say CDMA. I would say it's something known as a multi-carrier CDMA.
right, yeah,
So that's closest to this.
right. So what's the difference?
Well, the difference is in multi. So shall I talk about this first and then go?
Yeah.
So where this operates is, let me give you an example. So initially I have some data symbol, and I first multiply it with a CDMA code. Let's say this code has some 8 chips. So I have this 8 resultant chips. So now I have a transmission system which has some several subcarriers, and I have an option of how to put these 8 chips on these subcarriers. In this specific example which I have shown, I have used 4 subcarriers, and on each subcarrier I have placed 2 chips. So my entire symbol spans this time frequency grid. This entire shaded region is my data symbol, and each block is one OFCDM symbol. So in the literature of VSF-OFCDM, this operation of putting bits in 4 subcarriers is called frequency domain spreading, and this operation of putting 2 chips in each subcarrier is called time domain spreading, and I've written this here. And to go back to your question, in case of multi-carrier CDMA, they would put the same bits in one subcarrier, and they would put all the chips along one particular subcarrier. Yes, they do have a multi-carrier system. It's basically like multiple CDMA systems in each frequency subcarriers. But here I have the option of putting the same bit in different subcarriers. The chips resulting from the same bit in different subcarriers.
I think their scheme is as general as yours. There's no difference. The only maybe sort of thing that you have here is that you were constrained to OFDM, and I think their general assumption is that they have separate channels which are, bandwidth orthogonal.
I think the difference in his case is that his spreading sequence spreads both time and frequency.
Yeah,
They are the same thing.
Yeah, but I think they isolate
the way I understand
they build parallel channels
Yeah.
in time.
It's basically some n parallel CDMA systems.
No, right. The only difference is that, maybe you have OFDM, which is essentially overlapping in frequency. They sort of make sure that there are bandwidth difference, but in terms of signaling, there's no difference.
I think you're right that in terms of signaling there is no difference, but the choice of in his case, I think the choice of spreading sequence that's what makes difference.
No, they do the same. They can.
Because he will adjust as he will go. He will adjust this two-dimensional spreading sequence
So here I have the
for those
option.
dimensions according to the channel characteristics.
So
Well,
there
they
is a
could
fixed-
also adapt. There's no.
Well, probably
That's not a
in-
fundamental difference.
Yeah, in principle,
Well,
like in deployed multi-carrier CDMA systems, at least the impression I have is they put different symbols in different subcarriers and do spreading along each subcarrier. Whereas here it's a very adaptive factor. That's why we have this variable spread factor, the first part of the.
But I think we shouldn't argue about fundamental difference. Of course, I think fundamentally they are pretty much very similar, because they all do FFT, and on top of FFT they do some spreading. So fundamentally they are of course the same. Now I think the important contribution which Joydeep is doing is how to find these 2D sequences which tie nicely into specifics of a two-dimensional channels. So channel has a specific two-dimensional structure. He will utilize it to pick better sequences.
Sure.
You better go revise your slides now.
I think
That's not exactly.
I think I wanted Joy to tell me this.
All right. We will get that.
Yeah. So.
No, we don't want you to tell us now. We heard it. The timing there, so you do contiguous, but it could just as easily be non-contiguous, right, in time and frequency. So we could have little blobs all over the time frequency.
Yeah, but it's difficult in principle. Yeah, we could, but maybe that's simply receiver complexity. So I don't think they do it in their practical deployment.
It's not only that. He's trying to capture a unit.
No, I'm going to jump in there. It's his defense, so we want him to.
Yeah, in principle, that might be the optimal way to do. But I think in the systems which they deploy, they do it in contiguous. At least that's what I've seen in the papers. So there are just some points noting on the advantage of VSF-OFCDM. So the first thing to note is it's a diversity system, because I'm replicating my symbol in both time and along successive subcarriers. And as I said, a code multiplexing can be done in a subcarrier. Like those same, I can put another data symbol within the same 8 blocks just by using a different code, initial code. I can put another symbol there. So that's code multiplexing. And in most of the simulation, they do a prioritized time domain spreading. That is, they do not spread in frequency. I'm just talking about the commercial VSF-OFCDM deployment by NTT. And the reason they gave is that time domain combats frequency selectivity. And note that when they do spread in frequency, we get frequency diversity gain. And their simulation show that this system, such a signaling scheme, approximately achieves some 1.5 times higher throughput than OFDM for the same system bandwidth. There are some typical values, and the message that I want to convey is: look at the system, look at the subcarrier spacing. It's in the range of some 130 kilohertz, and an OFCDM symbol duration along time is approximately 10 microseconds. And these are the kind of channels they encounter, for which the coherence time and the coherence bandwidth values are plotted here. And if you see, the subcarrier spacing is roughly greater than the coherence bandwidth, and this means that the channel gains in different subcarriers are approximately uncorrelated. And the other thing which I want to convey is, if you see a symbol duration, and the spreading they do is they put 16 OFCDM symbols along one subcarrier. So the total time duration is this, which is also less than the coherence time. So we can say that along a time, all the OFCDM symbols approximately see the same channel. So these are the two key messages, because this will be important when
this is for outdoor.
Outdoor, yeah, all outdoor.
And
Pretty fast car.
Yeah, you did an upper bound on that, I guess, to show that it's constant even if the vehicle's moving very quickly.
Actually, I took this from their papers, the kind of experiments they have done. So these are the values that I
So
got.
it's a train. It's a train.
Yeah, because you see, like the vehicular speed is like quite high. I guess they have all their bullet trains and stuff like that.
They have a lot of landings, so they have.
No, I'm looking at that actually. It's like 300 miles per hour or 300 kph, but I'm pretty sure it's not 300 kmph.
kilometers is...
Oh, okay, so it's KMPH.
Kilometers per hour.
Ah, okay, so I remember making that earlier and thinking, oh, it was not objecting, but then I read
K
it,
should be lower K.
KMPH.
But the K should be
K
lower
should
K.
be lower K.
Not K, right.
That's what is confusing because it's like kilobytes.
Right.
Okay, so these are the two messages that I want to convey. That along a frequency, along successive frequencies, the channel is uncorrelated, channel gain, and along a particular subcarrier, all the symbols approximately see the same channel.
So do they assume this thing for outdoor?
C over 1,000.
Yeah.
The spreading outside?
Yeah. So now we are going to propose a conceptual model to analyze this scheme better. So in our scheme, we have a transmitted a symbol that we want to transmit, and we replicate this over NF subcarriers. And along each subcarrier, we spread the symbol with a CDMA code of length NT chips, NF and NT, and we multiply it with a power factor for each subcarrier. And since we assume that the channel was same for each subcarrier, along each subcarrier, all these NT chips are multiplied with the channel gain, where this edge could potentially be a distributed root of edge, and there is some additive noise. So for one symbol transmitted, I have a whole receive matrix, and the receiver does some processing to get a symbol estimate. And note that these edges are IID across subcarriers, which came from a previous assumption when you said the coherence bandwidth was greater than the subcarrier station. So I will just repeat this, whatever I said, because we need to remember this for the rest of the talk. I'll repeat it by taking blocks at a time. So as I've noted there, this is a power vector P1 to P of NF applied in each subcarrier, and there is a spreading codes given by this spreading matrix capital M. All these are the NF spreading codes in the NF subcarriers, and a code is of NT chips.
I have a quick question. So there's really no OFDM going on here.
Well, this is a baseband model. Like, you can possibly say that after this we have some FFT, but for purpose of our analysis, it's just a parallel channel.
So signal space model.
A signal space model.
But let me think of something else.
That's fine.
So again, going back to the channel, we assume a block spreading model where the channel is constant for a block of NT symbols along each subcarrier, in time constant NT symbols, and across subcarriers we have IID gains, H1 to H of N. And the models considered are, we have considered uniform fading model and a Rayleigh fading model, which we'll show later on. So some uniform, the channel for any block is given by this vector H1 to H of NF. We assume that the receiver has perfect channel state information throughout this talk, possibly due to some training sequence based estimation. As a transmitter, we have different assumptions. So initially we assume that the transmitter has perfect channel state information, possibly due to some receiver feedback. And then we take out this assumption. The feedback could be erroneous, there could be delay in the feedback loop. So we assume that at the transmitter just knows whether the channel is above or below a threshold. This we call 1-bit quantized. I will talk about this later.
Do you consider delays?
No, I don't. I just consider that the feedback might be erroneous.
You mentioned delays.
No, I said possibly due to delays it doesn't have perfect information. But I don't consider delays per se. But I just consider the general case that if this is the channel state vector, what the transmitter has is another vector, random vector U1 to UNF, and this is characterized by some joint distribution. So this is the most general case. The specific cases are when there is no information at all and when there is 1 bit of quantized information. So let's see what are the optimizing problems. For the single user, we consider two problems. One is the problem of ergodic capacity, that is maximizing the achievable rates over all channel realizations. And the second problem is we don't maximize over all realizations. We consider a given, a fixed channel realization, and see what is the optimal way to allocate power among the subcarriers. For the multi-user case, we consider basically a version of this problem, that is, given a fixed channel realization for all the users, what is the optimal way to what is optimal to allocate power to maximize the sum rates for that given realization.
Let me make sure I understand exactly what's going on here. So everything seems pretty standard so far. You have these random channel games, or are you going to assume you know them?
So initially, as I said, when the transmitter has perfect channel state information, we'll assume transmitter knows them, and then we show schemes where the transmitter doesn't know them or knows them with some error.
No, right, knows them with some, okay.
Yeah, but we assume that the receiver knows the channel at all times. Okay. So our these are our transmission equations. We have a symbol B which is multiplied by a code matrix capital M. It's multiplied by a diagonal power matrix capital P, and again multiplied with a diagonal channel matrix capital H. And if you see that these rows of these matrix basically correspond to my subcarriers, NF subcarriers. And along each subcarrier I have the CDMA code.
Excuse me, you multiply by channel to the power of half.
Basically, I mean, just
So
a notation.
Oh, that's just a notation. So you call your channel each one half.
Yeah. So, if we go on and write the mutual information between this matrix capital Y and this symbol B, we can go through the machinery, and this is basically what we obtain. We have this term PG of U, which is the power put in the jth subchannel, and as we said, the transmitter has access to U, so the power he puts is a function of U times the channel gain H at the jth subchannel. And if you see this summation over all subchannels, this is because I am replicating the same symbol in all the subchannels, so I get a summation. And this term can be looked as the effective SNR.
What is your channel is complex channel or real channel?
Here we have assumed a real channel, but
Real
even if we
channel.
assume complex, the formula would have held the same.
Yeah, so it's not.
We would have got a phase here, and this would have been, I mean, this formula would have been still the same.
So where does it, like when you derive all this, where do you use M? How do you use M?
Yeah, it's a good question. So basically for the single user case, the spreading doesn't really matter. So when I do all this, I get this M1 transpose M1 terms. I mean MI transpose MI terms in the derivation, and I've assumed unit norm codewords.
And you assume that they are orthogonal, right?
Yeah, and unit norm. So
Okay.
basically they don't figure out in the final result.
So they're orthogonal.
Yeah.
Yeah,
And that's some sort of assumption when you're spreading.
yeah.
On the chips, I guess.
Right.
But the message is for the single user they shouldn't really matter, and that's what we get, because spreading should not really give us anything.
So and they are also orthogonal even after you apply the channel matrix, which
Well, if you remember, my channel is fixed along for all the chips.
Oh, okay.
That's
so,
why. In the most general case,
so the
it-
gain is
yeah.
the same along this,
Yeah.
and therefore they retain
Yeah.
their.
In the most general case, it wouldn't be, but from the simulation we saw that was the model they considered. So these are the two problems which I was talking about. So first is the ergodic capacity problem of maximizing these rates over the joint distribution of U and H. That is, and subject to a joint power constraint which is averaged over all the states of U and over all the subcarriers. And the second problem is maximizing the mutual information for a given channel state H and a given channel state information the transmitter U. How to, and given that I am allocating a net power P bar over all the subchannels, how to maximize this.
What's the difference between the two? And what does the second one mean?
So if you see, look at this, here I am like, as I said, I am averaging over all possible states of U and H. So potentially here, if I have a very bad channel, I have the option of not putting power in any of the subcarriers at all. And if you look at this is a much harder constraint, that at each given channel instance, whether it's good or bad, I am constrained to pour P bar of power over all the subcarriers.
So two P bars I don't think are the same, are they?
We can keep them to the same.
You could, but actually I think the one is a sub-problem of the other. Like
That I can put it potentially as some P bar of U. Is that what you're saying? Over here? Yeah.
So my question is slightly different. You know, what are the two problems when you think of a real system and application, how do they relate and what do they mean?
Okay, so any scheme which will actually implement this will lead to very long delays.
So tell me about it, like why?
Okay, so basically if you see, this thing is achieved by what's called so-called water filling over time. That is, since when I said I average over the distribution, so the distribution means I will see at each time instant I will see the channel and see what value it takes and wait for a very long time so that all those possible channel realizations occur. And if I get a bad channel, I might not transmit at all and keep on waiting until I get a very good channel to put my power.
That's not a delay, each time you decode, I guess, for each.
No, maybe possible that I don't send anything at all, I'm saying.
So what?
I mean,
you might have to wait,
Yeah, I might have to wait.
That's not a decoding delay.
No, I mean the transmission process. I'm not sending anything at all. The transmitter might.
But you're maximizing some sort of average throughput.
Yeah.
So and you're sort of smart, the channel is bad, you don't transmit otherwise.
Yeah, it's true. So, so what exactly is the question? You're saying it won't lead to delays?
Well, the other one will also lead to delays because if you have a bad channel and you send something through it, then you're in trouble, right?
Why is that? He just reduces his rate and sends on the program.
But he reduces the rate here too, right? By reducing power, you reduce rate.
I think the difference between these two cases is that in first case he can wait.
That's what I'm asking him. I want to know what's the difference.
So here I'm not really talking about decoding delays per se. It's like, suppose I have a codeword to send over here. So there's a potential, like it's quite possible that I keep waiting for a good state forever. Because I have to average over all possible channel realizations. We are true that this might also lead, like if I have a very bad channel, I transmit something and I get very low rates and I have to transmit it again. But that's not really what I'm addressing here. I'm saying that here for each given channel realization, I'm transmitting something. And since, I'm transmitting something here.
I think to put it in simple terms, his transmit power in the second case, the total transmit power is constant. One in the first case, his total transmit power varies, and he actually auto-fills it in time. That's the biggest difference. So he has, in case one, he has more freedom to allocate his power.
So your problem in the second case is over frequency and the other one is over time.
This is both over frequency and time.
Right. And the other
whereas here it's just over frequency. That given a particular channel states in these frequencies and this total power, how do I put them in the different subcarriers?
But your each channel corresponds to what?
At any given block, I have this matrix, this vector of H1 to H of N.
But is that over time and frequency?
It's not about time and frequency. It's basically over frequency. That a given, say, if you remember, I said the channel is constant for a block of NT symbols. For such a block of NT symbols at some time instant, the different frequencies have gains H1 to H of NF.
What is NF?
NF is the number of subcarriers. Remember, each row of this matrix corresponds to a subcarrier.
And do you have a doubly dispersive channel?
Well, the channel model, as I said, was it's IID across subcarriers, and it was like constant.
IID across the block.
I don't see where the double dispersion is.
So there are two answers for this. The first is if we go by the NTT channel. So this was what they had. This is what the channel came out to. It's IID across subcarriers and constant across a particular subcarrier. The second way to look at it would be, like in recent years, there have been a lot of studies in signal design for doubly dispersive channels.
Right. So
and they have.
You understand my question?
Yeah, I do.
There's only frequency here. Where is the time?
Yeah. So the answer would be like.
I would expect instead of NF having some sort of larger end, which is
larger.
The one that combines frequency and time, because you have doubly dispersive channels.
Well, this model essentially is parallel subcarriers, but coming back to your question, like in recent years there have been lots of research on how to find basis functions for doubly dispersive channels.
Sure.
And they show that if we use signaling via them, this is basically a baseband model. I haven't talked about the modulation studies. So they show that if they use those sort of modulated symbols, even a doubly dispersive channel may be looked upon as a block fading model. I mean, we can...
Right, but it's blocks over time and frequency. It's not blocks only over frequency.
Yeah, it's blocks over time and frequency. That's true.
And you draw that square thing, right?
Yeah.
And you convinced us about this picture that I saw before. Right?
Yeah, that's true. But like, again, going back to the NTT system. So in that case, we can say their block extends over a sequence of NT chips within one subcarrier. That is the total bandwidth occupied by one subcarrier. So that would be a block in time and frequency. And essentially these would correspond to different blocks. Like if I go to the NTT system.
So you're not taking advantage over your diversity in time. That's my point. In whatever their proposed solution is, or your interpretation of their proposed solution.
Well, I look at these values and I say that my block extends over this sort of this kind of bandwidth and this time instance, for which the channel is initially constant. And when I am transmitting over several subcarriers, to answer your question, it would be I'm transmitting on several such blocks. So it's a diversity over this block. No, so I'm no longer actually thinking of time and frequency. There's this enough blocks which correspond to like different channels. Do I somewhat answer your question? Okay. So going ahead, so we first consider the case of a single user with perfect channel state information at the transmitter, and the receiver is assumed to have perfect channel state information. So for these calculations, I just substitute H for U, and I showed you these equations earlier, and this is what they become. This is the mutual information expression and the ergodic capacity formulation. So if we go on and solve it, so this is what we get. The solution is we should transmit in the best subchannel, which is denoted by Hn star. Here N basically means the number of random variables over which I perform this maximization. In our application, N is equal to Nf, the number of subcarriers. So for any given channel instance, I decide to transmit on that subchannel which has the maximum gain. And the actual power which I put in this channel.
Sorry, whoa, back up.
Go back one slide.
Yeah, back up just one slide, maybe we'll back up two. H is a vector, right? I'm bugged. It must be a conceptual thing. I'm bugged by it. Each one of those channels is orthogonal. They're different frequency slices, right? So what you're telling us is that the solution is to restrict yourself to the subset of the signal space, no matter what.
For each instance. That's because I was sending the same symbol in over all subcarriers. That's why. If I were potentially sending different symbols in different subcarriers, then the answer would be the classical water filling solution for parallel channels. But here it's the same symbol replicated across all subcarriers. That's why.
Okay, so it was a dumb. Okay, get it.
Yeah. No, actually, this was a confusion even we had initially when we were checking. So in this case, it turns out the solution is to transmit in the best subcarrier, and the actual power we put is got by averaging over the distribution of Hn star, which corresponds to water filling in time. And these are the equations that we get, that the power we put for any value of Hn star is given by this equation, where 1 over lambda is the water filling level, which is obtained by solving the total power equation, total power constraint. That the power averaged over all steady states gives the total power. So to answer your initial question, so this thing would not have been there if you just consider the second problem of maximizing rates for just a given distribution. And I guess in this case we can potentially get higher rates because we are not transmitting the bad subchannels and transmitting only in the cases that's good.
So you're not waiting for it. For each channel state, you decide what the power is.
Yeah. So so let's see what the effect of increasing the number of subcarriers. So that's basically given by the variation of this PDF, how it changes with the number of subcarriers. So just some typical examples. If each gain were uniformly distributed in the range of 0 to capital A, which is a uniform fading channel which you consider for simulations, the mean would tend towards capital A and the variance of HS star would tend towards 0. So the capacity would be that of a channel with constant gain, that's the gain of A. And if you consider that each of the square root of HS were rarely distributed, then the HS would be exponential distributed with mean of gamma of A. In that case, the mean of this maximum random variable tends towards infinity and the variance is finite. The capacity potentially keeps on increasing with number of subcarriers. So here we have some numerical results for the uniform fading case. A case capital 1. So I've just drawn the distribution of HN star. And if you see, the different curves correspond to when we took different number of subcarriers. So here we took 2 subcarriers and the red one corresponds to 100 subcarriers. So there are some standard observations that the mutual information value increases with the number of subcarriers because the higher gains are more probable. And the fluctuations in this sequence also decrease because, as I said, the variance keeps on decreasing as we increase the number of subcarriers. And also if we consider many subcarriers, then the mutual information, that is this given by this red line, red graph, approaches that of a channel with constant gain A. I mean, this value is nothing but this, and we can see that. So it matches our intuition. And these are the same graphs just plotted for 2 different values of SNR, where SNR was defined by P bar over sigma square, and we get a roughly 3 times better mutual information. So now we have the same results for Rayleigh fading. So I've just written down these 2 equations just for recalling purposes. So there are 2 important messages to be taken from this graph. Let's first see along any particular graph. Let's take this red one, which corresponds to a fixed n. For a fixed n, when the overall power decreases, that is when we move towards the left, I see that my lambda keeps on increasing. And if you remember, my transmission threshold was given by lambda times sigma square, so I have a high threshold. So what it basically means that if I have a low power, I better transmit only in the very good channels because I should not waste my power transmitting in the bad channels. So that's why the transmission threshold is increased. The other way to look at it is, suppose I fix my power, overall power, and now I increase my n. That is, I go from this blue curve to this red curve. Then again I see that the lambda is increased, which means again the transmission threshold has been increased, which means transmission is again taking place at higher values of channels. And the interpretation now is, since I have taken more subcarriers, there is a higher probability of getting a better channel now, because I'm considering more subcarriers. So these are the 2 messages. And again we have the numerical results for fading for Rayleigh. And approximately we see...
I'm sorry, just real quick, forget about OFDM, forget about the whole overall structure that you have. And I'm directing this to you, but also directing this to the zeitgeist here, the historical zeitgeist.
The thing is, I sometimes just look what the zeitgeist is.
Just the group, the group feeling of, the group kind of subconscious feeling of what's going on here.
Okay, that includes all the rest of you, I think.
So, this notion of picking the best channel has been around, I mean, at least 10 years. Pierre stuff way back when, kind of.
Yeah.
So that's right.
So it was for a different context. So in the knock and home result, there was a multi-user scalar transmission, and here we have a single user transmitting over single user vector transmission. And that was to maximize the sum rates. And yeah, they got a similar result, I agree.
Yeah, what I'm asking here is that if you strip away all the coding and things like that, essentially you're talking about the max over a set of IID PDFs, and
the mathematical model turns out to be the same. Yeah, I agree.
yeah,
So this part you can say fundamentally it's not new, and I would agree with that. But this was for different application, and we reduced it. We took the application, reduced it to the same model.
Oh, when you say and, it's for a different application, that doesn't impress me. I think you answered the question. The basic idea has been around for a while. You're applying that basic idea to your particular transmission.
That's true.
Okay.
That's true. And so now we have something which is new, hopefully. So if you take the same problem and you consider colored noise instead of white background noise, and this a possible source might be the multi-user case for the interference from other users as treated as noise. And we have the same channel gain vector, and let's assume that channel gain matrix H, which was basically diagonal with these vector as a diagonal, and the powers P1 to P of NF. Then we found out that optimizing the mutual information for a given channel state H reduced to maximizing this problem subject to this constraint, and this is essentially in the form of some X transpose A times X with X transpose X equals to some constant and X greater than 0 because the powers had to be positive. And this turned out to be a non-trivial problem to solve. And in the thesis, we developed an algorithm with exponential complexity. And when I say it's non-trivial, this is made more clear with this example. Like let's consider a case and see why it's a problem. So this is a problem that I've stated. And let's consider a two-dimensional case where X is given by this vector. And what I have plotted here is, these are the matrices A. And what I have plotted is X transpose AX versus X1 and X2 only for these boundary regions where X transpose X equals 1. That is given by this nice line over here. And if you see in this case, there can be multiple maxima at the boundary points. And that really depends upon the structure of this matrix. If we just rotated the eigenvectors and came to this matrix, then we saw that the maximization point, there would be a unique maxima somewhere in the middle, corresponding to this eigenvector.
I'm losing it, Roy. I did exactly this thing, plotted it out. I would never have thought it looked like that. Alright, so I'll just believe you.
I just plotted them for the boundary points. X transpose
I
equals
did exactly the same thing.
You got the same result?
Hell no. But that's just, I think I must have made an error. I'll do it
So you
again.
can verify this. I verified
So the
this.
thing is, did you plot the surface with X transpose X
I did both.
over the disk?
I did both, and I also parametrized the things, but I looked only at a parameterization along the boundary. I didn't get anything that looked like that, but that's a very mean and nasty thing to say, because I wouldn't stand up and bet my pinky on it right now. This is your defense, so I'll go and check.
So I think he's right, because we had our whole email discussion about this, and this is the picture I've had in my head, and so I told him yesterday, you really ought to have a picture just to, right, and his picture looks like what I was expecting. And it's very nasty because you get two local maxima, right?
Well, let me make sure I'm seeing what you're seeing. What I'm seeing is if I parameterize along the equal power line,
This one?
the constant norm line.
Yeah.
I do this.
No, I don't know what that I think that's some artifact, isn't it?
Yeah, it's a MATLAB plot.
Oh.
The up and down.
Okay, good.
The only thing that matters is that's the envelope. Yeah, just look at the envelope.
Okay, all right.
Just put it.
So now, all right, go ahead. Now that I'm not freaked out, what are you telling us? Okay, now that we're looking at the envelope, you're saying that there's a problem.
So I'm saying that it really depends upon how the matrix is.
Yeah, right.
For this matrix, I get multiple maxima at the boundaries. And if you remember, that's a 2x2 matrix.
This multiple is just blowing me away. What do you mean multiple?
I mean, these 2 points, 1, 0, and 0, 1, both give the same value of maximum, which is 5.
Yeah, they're on the boundaries.
No,
Yeah,
no,
so
but
the problem is we cannot really solve this using standard convex optimization problems like hill climbing.
Hold it. Let's look at the, just the, let me just make sure I really understand what's going on. That's an artifact.
Yeah, let's consider that.
Floating MATLAB.
Great. Okay, so I look at that. If I looked at that, basically I see a paraboloid or something that looks like that. Why can't I hill climb on that paraboloid? So I go, so I hit that one. So what?
So, okay,
but
so
you're not
the
guaranteed
definition of hill climbing is you get to a certain point and you look in your space of feasible directions for a place to go further up the hill.
I'm looking there. Looks like I
So-
can go up the hill.
But you are not guaranteed to reach that.
So what happens is, depending on how you twist this around, you could climb the hill up over here and reach this endpoint.
Which
Right.
is good for that particular set of matrices.
No, but so you reach that endpoint and then you declare, oh, I guess I'm done, right? But you're not certain to have found the global optimum. Because it might be that the other direction, you could climb the hill in the other direction and reach this other local
Isn't that
maximum.
a corner?
Okay, for this
Wait.
The point is,
I'm sorry now.
Okay, so let's just say,
explaining.
okay, so you start
I'm not
somewhere and you
really.
start climbing the hill in whatever looks like the gradient or choose that direction.
I hear you.
You'll eventually say climb up into this corner.
Right, that might be too low. Gotcha. But that's
Right.
isn't
And
that a standard issue? Isn't that a standard problem with dynamic programming, finding the right corner?
No, so if you have problems where you have, so the key is this thing, right? Is once you're in a corner, right? The only way to go out of that corner, right, and stay in the space of feasible solutions is for your objective function to go down,
Gotcha.
right?
That's fine. But my point is there's some number of corners in this problem. You take it up to multiple dimensions, right? And isn't that one of the standard optimization problems, searching the corners?
That's exponential.
That's exponential, that's
Yeah.
the point. All right. And that's
So here's the thing, in general it's exponential, but I am not so convinced that on this particular problem that you actually have to have a search of an exponential number of corners. Like it's just that no one at the moment, and maybe one of you guys can point to a reference that says, oh, this class of problems with the positive definite matrix A, X transpose AX, necessarily has to have exponential search, right? Take up a reference, and sure, somebody must have analyzed, right?
So
All right, guys, thanks for
this
educating me.
is we have a solution for this problem for any general name, and that is exponential. For any general name. So we develop a solution.
I mean, there are conditions on A. I mean, let's say A and all the submatrices of A all have different eigenvalues. I mean, we analyzed it quite a bit, and I mean, there are certain cases in which we can say that we don't have to search all the exponential cases. Like only like if let's say all the eigenvalues of A are different, and there is one positive eigenvector which is in the there is one eigenvector which is in the maximum eigenvector is in the positive.
Oh, yeah, that's the best trivial case.
Yeah, that's
so
what I'm
when
just-
you coincide, right, with the Rayleigh quotient, because the optimal solution to some relaxation is in the right space. Great.
So I think the other people are not really out of context, so we can take this offline. Because it's some problem which some of us have been discussing exclusively before, so we can do that offline.
Like my question is, like, if you look at the border, is it that sometimes it's concave, sometimes it's convex?
You mean at
When you
the...
plot it.
Yep, which is
Yeah, what are
confusing.
No, I'm just asking, is that right?
Yeah, it's just a...
Are those the only two options, or you can have a combination? Can you show that?
Probably.
There can be, but for a 2x2 case, I think this is what you get.
Can you have a saddle point here?
Right, that's.
So that's neither convex nor concave.
Well, what he really has is if you go into the diagonal coordinate system, right, of the eigenvectors, right, you have a convex function, right, because it's just the sum of squares with the eigenvalue weight factors, right. But then you get some conditions, right? You get a bunch of linear constraints that what was the positive working gets translated into a lot of ux greater than or equal to.
It is a convex function, but not necessarily convex.
Yeah,
over-
so
But it's convex, but it's
That's right.
But not necessarily over convex.
no, the space is convex too.
Oh, space
right?
is also-
But what you're doing is you're maximizing this. You're minimizing. You're maximizing it, and you end up in one of these large number of corners, right?
But I think then in that case, back to Chris's question.
to go back to your question, if I plotted it for all the values of x,
Convex function over
it's something like
convex whole.
goes.
So it's just if you were trying to
Something better than
minimize that,
exponential.
right?
No,
Your
it's only
life
to
is
look at
great.
min. You're getting-
It's a difference, I always get this wrong, because they always say convex or concave, and I'm never sure which I mean, because I always mean either one, right?
Uh-huh.
But there's one of those key places where it matters.
Oh, it
Like if
matters.
the function were concave, right, then it'd be like, you could always
It's the
apply.
capacity maximization,
Yeah.
capacity thing. Water filling.
So now we come on to the domain of multiple users, and again we assume perfect channel state information both at the transmitters and at the receivers.
When are you going to tell us about random H? Or did I miss that completely?
Just a second. Yeah, what is it?
Well, when are you going to tell us about random H?
Random?
Yeah, you said something about you're going to estimate H and,
No, I didn't.
I'm
No, that's
hallucinating.
that's someone else's. Yeah, we assume either we know the H or we know it with some error, but we don't go on to estimation.
All right, and where's the with some error?
That's coming.
Oh, coming,
After
okay.
this.
Did you compare the results for the two optimization problems?
Which two optimization problems? With perfect and.
No, with the MMI and the regular.
So for this case, we didn't consider the MMI. The MMI we considered for cases where we could not directly do the ergodic capacity formulation, like the multiple users or like some cases, basically for multiple users. So these are the equations for the multi-user system. Assuming I have some capital N number of users in the system, and each one has this information capital BI times the spreading matrix MI and power matrices PI and channel. So if my metric is to optimize this mutual information between this received matrix capital Y and the vector B for a given channel instance, that I know these, the transmitter knows these matrices. So if I want to maximize this mutual information over set of all power matrices and all spreading matrices, it's a difficult problem to solve. So what we do is we consider some special cases, specific cases of this general problem and see what insights we can have. So the first case we consider is when we consider only time domain spreading, and that is we consider only one subcarrier and spreading along the subcarrier. So this is what the model reduces to, and then we find that this problem has already been addressed in the literature, and solution is given in this paper. So the solution is, let only the NT users, if you remember NT was the length of this spreading code in time, let only the best NT users transmit using orthogonal codes, and the power allocated is obtained by autofilling over time. So in essence, this reduces to NT parallel Goldsmith-Varia system because they are using orthogonal codes. So this is a solved problem. Now we consider the other case, that is,
What's NT?
NT is the length of this CDMA code in time, NT chips.
Also, M is larger than MT.
Yeah. I mean, if N was smaller, then I can give everyone an orthogonal code and be fine. So even if N is larger, they say, then also let only the NT best users transmit, if I want to optimize some capacity.
You didn't tell us.
Yeah, right.
Now I'm a little confused. Wouldn't the NT chips spread across?
No, I'm just saying
Oh,
only
now
time
you're fixing
domain.
the F.
I mean, I have just one subcarrier.
Got it.
This is a special subcase. And the other subcase would be not to spread in time at all, but just consider along frequencies. So I have only frequency domain spreading. So this is what my model is. So the mutual, so again, I'm considering the MMI maximization problem. That is, I'm given instances of these channel gains. So the expression for mutual information turns out to be this, where I have, so if you look at this, this is essentially the sum of the
Alright, so you have
covariance
n symbols,
matrices.
you have n symbols that you're spreading over n channels,
Yeah.
right? Okay.
Yeah, so the covariance matrices, and this, the sum of the covariance matrices, and this is what the problem is.
And the thing you're choosing is power, so
Yeah.
okay.
So if I go back in again literature, we see that similar problems have been addressed to in where you call it multi-user vector transmissions, and the optimal solution is water filling over interference plus noise spectrum. However, such techniques are not applicable here, because if we again go back and examine our problem, we'll see that our transmit symbol is this, which is essentially rank 1, because of the fact that I was replicating the same symbol across different subcarriers. So my transmit covariance matrix is a rank 1.
Sorry, I gotta really stick with this here. So this B sub I now, that's
For the
a
IC
Mac problem, or we are Macking now, or we're one user?
Mac.
We are N users, capital N users.
And each user has
symbol.
has one symbol.
Yeah.
Okay.
Which replicates across all subcarriers.
Done. On the symbol you're done.
Yeah. So this replication makes a transmit covariance matrix rank 1. So essentially I'm not using my entire signal space, and so this is not a convex problem. And in fact, a very similar problem is in your book, in Professor Rose's book, and it's been shown that it's still not solved. So what's the lesson that we take from here? I mean, the lesson I think is it's difficult, like we should have a different approach rather than some capacity maximization. Like,
it's funny, you say that the different approach is to not be a nudge and make sure that everybody has one symbol, let them use multiple symbols, and then they can spread over the whole spectrum.
oh yeah, we can do that, but that again, I mean, it's
Right,
something like a
right.
multi-code CDMA, which is
Yeah, if you're putting yourself into the box that it's one symbol, then yeah.
Yeah, but we did that because of, again, their original model.
Understood.
Yeah. So, another way to answer that question would be, when they put the same symbol in different model, what was the basic motivation? That was one of diversity. I want diversity again. And the cases we have considered till now is when that transmitter has perfect knowledge of the channel state. And we know that if that is the case, diversity doesn't really bias anything. So all that advantage would potentially show up when we consider the case when the transmitter doesn't know. But yeah, for this case, it's much better to transmit different symbols in different subcarriers. So the different approach would be to consider some comparative optimality and some game theoretic considerations. People like Farad, who gave a talk here, address similar problems but from a different optimization matrix. So since we don't know what the optimal is, we propose some heuristic schemes for the multi-user case.
What is competitive optimal?
It's like saying each user tries to do as best as he can, and each of them reaches some sort of equilibrium point where no one of them can do better by increasing his or her own power. But that need not be a global optimum. Like a similar problem as in the interference channel. There also the optimal information theoretic is not good.
Some sort of distributed solution.
Yeah. Each user tries to do really as best as they can, which is some equilibrium. And so we propose some heuristic schemes, and the main motivation is the ease of implementation of the schemes. How easily can we implement? And we provide explanations for the two user. We consider a case, special case, 2 user and 2 subchannel case, and see how best to allocate power. And again, this was the matrix, the sum of the covariance matrices for the 2 users. So the first heuristic is called optimal single user transmission. That is, each user individually chooses to transmit in his own best channel and does not consider the effect of the other user at all. So if Hij is the channel gain of the ith user in the jth subchannel, so I have these 2 random variables. This is the user 1's best subchannel, and this is user 2's best subchannel. So if we go on and see what the mutual information expressions are, that really depends on whether both users are transmitting in the same channel.
You know, it just reminded me, I completely forgot, if you do allow everybody to spread however they're going to spread in this sort of dispersive channel, this OFDM sort of model, they're going to naturally segregate. That was one of the results.
So what do you mean? What naturally?
They will naturally segregate. There's a condition on the way you derive this, and just like everything else we do, you forget it after you don't use it anymore. But if the ratio of the channel gains is
but
the guys naturally segregate.
But here I didn't have any spread. I just had two users.
No, wait. I'm not finished. Given that the optimal thing, we know that the best you can do is to allow everybody to spread everywhere and let the chips fall where they may, and that maximizes thumb capacity. If you allow that to happen, they are naturally going to segregate, assuming that the channel gains aren't.
But I think that's again when I allow a person to transmit in the entire signal space.
Just hold on. I'm working my way towards something. So again, the optimal set of things to do is if I can spread everywhere, what I'm naturally going to do is one of the users is going to end up in this two-user case. One of the users is going to end up in some subspace. The other user is going to end up in another subspace, and they will overlap on at most one channel. That was the result. So taking that notion, if it's optimal to segregate, one possible solution might be to figure out what that segregation should be, and then do your single user stuff, figure out which of those available subchannels in the segregated space is best for each user. But I don't know whether that works for this case.
And that might be interesting way to for future direction, I guess. Yeah. So here
Roy, do you remember this? Probably not. If I don't remember it, you probably don't remember it.
No, that's what I was asking.
Okay. Yeah, it was Dimitri's stuff early on. And we ran up against exactly the wall you ran up against. We decided we were not going to be bold like you, and we took the low road and said spread.
Yeah, but I think you consider multi-code CDMA after that, right? If I remember your book rightly.
It's the same notion. I'm just allowing spreading.
Everyone to transmit the entire signal space.
Right.
But I don't do that here.
All right. Maybe I'm not being clear. I understand that.
Yeah.
Okay. But if you allow everybody to spread, they will segregate.
Okay.
That is optimal. So we know that's optimal given all the degrees of freedom that you can possibly have. The sub-question there that I would ask is, given that, well, here's one space, here's the other. Well, since you're requiring people to use only one code, this guy might work in this space, pick the best channel in this space. This guy might pick the best channel in his own space. And that might be just as good or better. I don't know. That's the question. It might be just as good or better. Or
Yeah, look at it. So, coming back to our system. So, basically, the mutual information expression depends upon whether they transmit in the same subchannel and leads to interference, or they transmit in different channels. And as I said, it can potentially lead to interference. The advantage of this scheme is it's very easy to implement because each user is just considering his own channel.
I don't think it's now like I think about that now. It seems like maybe it's not so easy, right? Because implicit is the idea that like, oh, you choose your channel, I choose my channel, but like how we're going to code depends on what we chose. Like, so you look at the expression, we transit in the same channel, right? We're not going to use the same code as if we transit in different channels.
Right.
Like the coding over here, like.
The range is not too different here.
I guess what I'm saying here is I think you created by n equal 2 channels, an artificial snake pit.
But this is the sum rate, right?
Well, yeah, I'm just saying it's
individual
easy to implement the mathematics of some mutual information calculation, but the real implementation, right, is maybe not so simple.
Well, at least the part where in which channel to choose, the initial decision, that's simple. Because I am neglecting the effect of the other user already. But yeah, you're right. When I go on and calculate the rates, that might not be so easy.
Can you show this converged?
And
no, it's just a heuristic, right?
Yeah, cool.
Right.
If you do the simulations and it kind of converged or not?
Yeah.
And what do you mean by
I
converge?
was looking at, maybe I'm skipping ahead. There's an algorithm where you do it in an iterative fashion. You treat the other guy's noise.
Oh, it's this one.
Obviously, I am jumping ahead. All right.
Yeah.
So you'll tell me that it doesn't converge or.
So the second heuristic is to treat whatever we have from the other guy's signal as noise, along with the background noise. And if you see, this is similar to that single user colored noise case which we had a long discussion some time back. And this is the same problem replicated over here, that each user chooses this power vector to maximize this expression. And if you see, this is his channel gain matrix times the interference plus noise matrix due to all of the users. And again, if you talk about the implementation issues of this scheme, this can be done by the receiver broadcasting the entire spectrum to all the users, and since each user knows what he is transmitting, he can just subtract it from the entire spectrum to get his own noise plus interference. So this is the second heuristic. And the third heuristic, we say it's called optimal single dimension. So by this I mean that a user transmits in only one subchannel, but it need not be his best, because if we consider two, let's give an example. We have two users, both of them have the same best subchannel. So if they both decide to transmit on the same subchannel, it can lead to interference. But it's possible that the first user's second channel was only marginally less better than the first one, so we would get a better rate by letting him to transmit in the second channel. So again, just for a two user two subchannel case, we can, it's simple. I mean, we have 4 possible combinations, and we can work out the rates for each one of them. And the claim is we pick up the one that's the highest. The problem with this scheme is this does not really extend easily for higher users and higher subchannels. So I have some numerical results over here. So this is the mutual information achievable along with time. And if I see these circles, these are the optimal single user, that is each user transmitted only in his best subchannel. The green line is when the interference was treated as noise, and this is after 5 iterations. I didn't mention it here because that process of treating other interference as noise has to be done iteratively. This is results after 5 iterations, and these triangles, if you see, is the optimal single dimension transmission.
Why 5, why not 10, why not 100, why not 2?
But for the two user two subchannel, I saw that 5 was like, we did not get any more gain by.
It looked like it was converging after 5.
Yeah, it looked like after 5. And we see that treating the interference as noise seems to do pretty well as compared to the single dimension policy. And we can't really claim if it will extend to higher cases, but this is just a possible indication. Because treating interference as noise method was easier to implement than the optimal single dimension policy. And at least heuristically we have some indication. Okay, so now we move on to, we again come back to the realm of single users, but now we consider imperfect channel state information as a transmitter. And let's see what's the optimal resource allocation that the transmitter can do. So again, I have shown you these equations previously, and just for sake of recollection. So the actual channel state is given by this vector h, and what the transmitter has access to is this vector u. So it allocates power as per u and not h. And this is the ergodic capacitive formulation. And the solution really depends upon the conditional density. If you see, conditional density of h given u. So there's some math details. If I just write down the Lagrangian and try to see what the solution is, I get these two equations, where this term I can call the effective subchannel seen at the effective value of the channel seen at subchannel j. The actual channel gain is just h of j, and this gives an indication of the effective channel seen at subcarrier j given channel state feedback u. And that will become more clear in the later slides, why I say so. We can't really get much intuition from this equation, so this perhaps will make it more clear. If you remember, lambda, which I had over here, is related to the water filling level. If you remember, for this case when there was perfect channel state information transmitter, 1 over lambda was the water filling level, but in this case I just say that lambda is related somehow to the inverse of the water filling level. and this I call the effective subchannel seen at the receiver J. The maximum value of this quantity set is got by setting all these terms to 0, the power values to 0.
Could you tell us whether this problem is convex, concave, or whatever?
He's looking for local minimums, for local optimization. Real. Yes.
Well, this, I mean, well, this, since I'm doing I mean, this is a concave problem. This can be solved using Lagrangian. I mean, I don't show it.
You know that?
Well, this problem, okay. So the similar problem had been done by Kaire and Shamayan, but they did it for a single subcarrier. So I extend the result for multiple subcarriers. So they showed, so they had the same problem, and for them they showed that such a method holds.
Did they show that their problem is concave? Not
Yeah.
convex? They did?
Yeah.
And
So-
is yours?
Well, I didn't show it explicitly, but
But you're not sure.
I mean, I think it can be shown. It shouldn't be a
That's,
problem.
yeah, he's laying a trap for you. So you fell into it already. The answer is, I don't know.
I don't know.
Thank you.
Okay. So assuming for the moment that it is.
But why do you need to assume that it is? You are looking for a stationary point. So just tell what you are really doing, and you are finding a local extremum of this function. There is nothing.